This video focuses on plotting equations of the form Ct is a function of r that describe the motion of massless particles such as photons in the equatorial plane of a Kerr black hole. It then investigates the shape of the local light cone in the region outside these black holes. Alright, so in the previous video we found the following relationship between coordinate time and the radial coordinate of an outgoing photon in the equatorial plane of a black hole. And that was the subject of all that algebra in the last video. Now the ingoing case is found by multiplying this by -1, so minus Ct, so it gives us this form. Okay, this is being the outgoing form, and then the ingoing, describing an ingoing photon, is this form here. Now, as an example, let's plot both of these cases, ingoing and outgoing, for a 1 billion solar mass black hole with a dimensional spin parameter A star of 0.8. Just remind ourselves that mu is gm on c squared, mu here. Gravitational constant times the mass of the black hole over the speed of light squared, and the spin parameter A is gm on c squared times A star. A star is a dimensional spin parameter. It's varies between 0 and 1. And that tells us that mu squared is greater than A squared. Since this A is less than 1, this A squared then will be less than mu squared. Okay, from delta equals 0, the event horizons R plus and R minus. The outer event horizon in red, the inner event horizon, cosine horizon in green. All right, so plotting the ingoing in red, the outgoing in blue, okay, and the two event horizons, the outer R plus, the inner R minus. We're plotting this on a space-time diagram with Ct and R as the two axes. Now we can see for the ingoing photon, it asymptotically approaches the outer event horizon. You're getting closer and closer and closer, and for a distant observer appearing ever more redshifted. And then between the two event horizons, we have this one. Space-time axis flip in this region, we'll talk about that later. And having crossed the outer event horizon, the only direction in the future the photon is into the singularity. Now let's remind ourselves the Kerr line element and Boyer-Lindquist coordinates is this object here. We're going to use this to investigate the local light cone at any point. Now, in this whole section for these last few videos, we're just dealing with the equatorial plane of the Kerr black hole. And so, for a photon in the equatorial plane, at any point in that equatorial plane, what is the shape of the light cone? So let's have a look at that. Well, the equatorial plane theta is pi on 2, d theta is 0, d phi is 0. We're just going to pick a point, and we're just, what is at that point, what is the shape of the light cone? For photons, ds squared is 0. So from that, from the line element, the Kerr line element in Boyer-Lindquist coordinates, the only two surviving terms are these two. ds squared is equal to this, it's equal to 0. All right, we can do some algebra and rearrange this. So 1 on c squared dr dt all squared, or dr c dt all squared, is this object here. Okay, let's simply take this first term, put it on the other side, divide through by c squared dt squared, gives us this bit here, and we're left with just this. Okay, and then multiplying across by the reciprocal of r squared on this to give us, which is this object here, multiplying that. Anyway, doing all that, establishing a common denominator, or writing this here, we've got, okay, here, common denominator, we end up with this, because we have this times 1, that bit there, this times this bit over here, it gives us r squared here, the first term. Then over here we're going to have r cubed, because r squared, r, and the c squared, so it's c squared r cubed. So forget all those comments about common denominator, I'm not doing that. And then I'll divide through here, r squared on r squared is 1, and so on here, just dividing through to establish individual terms. And the reason for doing that is we're going to have here 1 minus this, then we're going to have 2 minus 2 mu times this, so it's plus 4 mu squared on r, that goes there, plus a squared on r squared minus 2 mu a squared on r cubed. And remember, mu was gm on c squared. And so here, we can factor this as 1 minus 2 mu on r all squared, and then the last two terms on the end here, which is very handy. Next bit. All right, so that gives us that dr c dt is plus or minus square root of all of this. All right, now far from the source mass, but still in the equatorial plane, so just moving further out, this in the limit as r goes to infinity, this object here in the limit as r goes to infinity, all of this just reduces down to plus or minus 1. And so dr dt, remember dr c dt is plus or minus 1, so dr dt is plus or minus c. So far from the source mass, the local light cone is the usual one of special relativity of the flat in the flat Minkowski space. What's interesting about this is that in the limit also, if we look at this here, in the limit as a goes to 0, we recover the same relationship for the Schwarzschild case. So we recover the Schwarzschild case is what I should say. So in the limit as a goes to 0, these terms drop off. We get the square root of this, which is plus or minus that, plus or minus this bit here. dr dt is plus or minus c times r on 1 minus 2 gm on c squared r, which was the shape of the local light cone around the Schwarzschild black hole. And that too in the limit as r goes to infinity gives us plus or minus c, as you can see in all the videos in the Schwarzschild playlist on this channel. All right, so let's have a look now at the light cone. Bearing in mind at infinity, far from the source of far from the rotating black hole in the equatorial plane, we have, well, anywhere even outside the equatorial plane, we have dr dt is plus or minus c. Okay, but in the equatorial plane, close in or closer in, less than r infinity. As we get closer, this relationship here applies, and the light cones, as a result, as we move in, close up. Just so they did in the Schwarzschild case as well. They close up. We plot that here. R plus is the outer event horizon, R minus the inner event horizon, and you can see they just close up. The blue lines are the outgoing geodesic, the red are the ingoing geodesics. Between them, it reveals the shape of the light cone, as in special relativity, where you've got the outgoing right-leaning diagonal and the ingoing left-leaning diagonal. That gives you the shape of the light cone with a 90-degree angle between them. And the same happens here. And the same thing, as we move in, the light cones close up as we get closer and closer and asymptotically approach the outer event horizon. Right, now, between the event horizons and the ring singularity, the time component, the time-like component, GTT becomes outside, far from the source, outside the source mass, GTT is negative, but once you cross the event horizon, in fact, once you cross the stationary limit horizon, this GTT goes positive and becomes space-like. And the space-like component, GRR, becomes time-like. So these swap roles. Right? So the spatial component becomes the time-like component, and the time-like component becomes the spatial component. All right? Outside the event horizon, moving in this direction up is in increasing time, positive time direction, and okay, this is the spatial direction, and then they swap roles. So what happens is that the light cones flip over. So that for the particle here, if we look at this one, for instance, the blue curve is the outgoing, the red is the ingoing. You can see between them, the light cone is pointing now towards r equals 0, the singularity. The future of this photon is at the singularity. And the light cones have flipped over. We're moving in towards the singularity. And that's it. Finished with that one.